so I haven't gotten them done yet.
Just be helpful for the test.
Yeah, of course. Which test?
The take-home one for next Thursday.
Oh, really?
Just for the series.
Oh, for the series ones. Oh, okay. Yeah, I see your point. Yeah.
I did very well.
I see. Yeah. I'll work on getting that put together for you guys soon. So, I'll begin with a word of prayer. Dearly Father, we thank you for this day. Again, Lord, I thank you for these students. Pray you be with us today. Help us again, Lord, to glorify you in what we do. In your name we pray, Lord Jesus. Amen. Yeah, I know you guys are probably down. I know she lost. It's sad, but let's see here. Okay, so variation of parameters for systems. I don't know. So you guys are young. You may still labor under the delusion that government helps people. I don't know. I want to divorce your intentions from reality. Let's see here. Anyway, dx dt equals to ax plus f. This is our goal to solve this thing, where f is not equal to 0, okay? So this is the non-homogeneous problem. Here A is a constant n by n matrix, right? So we already know how to find solutions to the homogeneous problem, all right? So we already have, we can construct x, right, which is x1, x2, xn, the fundamental solution matrix, right? If the matrix A is diagonalizable, we just find eigensolutions and paste them together, right? Could be sines and cosines, could be a complex eigenvector. So we get, real and imaginary parts, put them together. Anyway, we get this matrix, n by n matrix of functions that's linearly independent. If you like, you could use x equals to e to the at, right? That's a fundamental solution matrix. So here's the method of variation parameters. We propose that the particular solution, all right, has the following form. X times v, where this is some unknown at the moment, vector of parameters. And our claim is that that's a sufficiently general guess as to solve this thing, all right? So what do? You make a guess to a differential equation. What's your next move? Your next move to figure out if that guess is reasonable or not is you take this, right, and you plug it back up into what it's supposed to solve, right? Let's call it star. So dxp dt, right, well that on the one hand is going to be ddt of x times v, all right? And that's supposed to be equal to what? That's supposed to be equal to ax plus f, right? This is our goal. This equality is the goal. All right, so let's see how we get to that goal. So this, by the product rule for matrices, is dx dt times v plus x times dv dt. All right, so I'm going from here to here. Then what? Well, x is a solution matrix. What's that mean? That means that dx dt can be rewritten as what? That can be rewritten as a times x times v plus x times dv dt, right? Well, this is wonderful, right? Because you notice that our goal is to show that this is equal to a times, this is xp, right? So what's xp? Well, xp is big X times v plus f, right? So this is our goal. That equality is our goal. And you see it's a goal we can reach because all you got to do is cancel this guy and this guy. And then you can solve for dv dt is equal to x inverse times f, right? multiplying by, how do I know the inverse of this matrix X exists? Well, it's a fundamental solution matrix, so it's invertible, all right? It's determined it's non-zero. And then here we're in the home stretch now, so that means that V, integrating both sides, we get V is equal to the integral of X inverse F dt. So in total, the particular solution we can form from taking the fundamental solution matrix X and multiplying it by the integral of the inverse of the fundamental matrix times the inhomogeneous term, the forcing term, dt, and there you go. That is a prescription for how to calculate the particular solution for a inhomogeneous system. Just like that. Now, to actually execute this for a specific example is, a little bit involved. I'll show you one here in a second. I won't write it out. I'm just going to use the projector. There's a lot I need to use the projector for today. I hope it works. So I was a little bit dicey. See here. See if it'll recognize. See, I got my voting sticker. See. Actually, I'm very happy because I was thinking about it. I was kind of worried, right? Because if this election had gone sideways, I would have had to get rid of this sticker, because it would have been a sore spot for me. Well, not entirely. I was for Cruz, so I would have just been like, "Told you so." But did I get a Hillary one? No, but I would have to get a Hillary one. It would have said pay to play or something like that. I don't know, but I actually was one. I always said as soon as Trump got in, I thought he could win, just because he's so unfazed by the media. And the media, let's face it, is really just invested in getting the Democrat to win because they're Democrats. I mean, we now have pretty explicit proof of this. Not only that they do this, but the mechanics of how they do this in terms of email chains and so forth. Thank you, Julian Assange. But and others. Let's see here. But anyway, I guess it's not that surprising. Come on. Where'd you go? I can find... No. Ah, here it is.
Okay.
Yeah.
Could you explain on that second black line at the bottom where the A came from?
Sure. The A here, right here,
The other side.
this one. So this, right? X is a solution matrix. So these are solutions. And remember what it means to dx dt is equal to dx1 dt, dxn dt, right? But these are, each column is a solution. So that means that's ax1, axn, right? And then by the concatenation proposition, we can pull the A out, which gives me AX. In other words, a fundamental solution matrix is a solution matrix. That means when you differentiate the matrix, it's the same as if you take the matrix and multiply it on the left by the coefficient matrix. That's part of the rights and privileges of the solution matrix. So, and here's why. That answer? I mean, that's what I did. I traded dx dt for A times x. I can do that because x is a solution matrix.
A is also a constant, matrix. So.
Yeah. So of course I went over these things the other day, but it's still, I know, it takes time for it to really sink in, which is fine. Let's see here. I think you guys, I think I'm close enough. You guys see it? All right. Oh no, oh no. I think I don't have my laser. You guys don't happen to have a laser on you, do you? Nobody carrying around a laser? I once asked that, not thinking I would get a response, and then some guy handed me a Soviet military grade green laser, and It was really something. It burned my retinas for that day. I'll have to make do with markers. Let's see here. Okay, here we go. So here's a problem that's inhomogeneous. I'm going to solve x prime equals to ax plus f. There's supposed to be a vector there. Oh well. Well, you can put vectors on the f's. You'll feel if it makes you feel better. Anyway, so this is a relatively innocuous inhomogeneous term. It's just 1, 0. So first order of business, I have to construct the fundamental solution matrix. This problem happens to have a complex eigenvalue of plus or minus I. So you get sines and cosines. Bam, here's the fundamental matrix. Cosine, minus sine, sine, cosine. That happens to be a rotation matrix. But anyway. So what's the derivative? Oh, excuse me, that's not the derivative. The inverse of the matrix is this. I flip the diagonals, which is kind of hard to notice. And I put minuses on the off diagonals, that you can see, right? Minus sign, minus minus is plus. I divide by the determinant, right? The 2 by 2 matrix inverse formula. The determinant here, though, is cosine squared plus sine squared, which is 1. So that's the inverse of that, all right? And now I just use, so this piece right here is the homogeneous term, right? So that's a linear combination of the first and second columns. This will give us like C1 times this, C1 times this plus C2 times that vector. So that's the homogeneous piece. And then over here is the thing we're learning just now. So the inverse matrix times the inhomogeneous term, which here was 1, 0. You multiply it, you integrate it, and then you still have to multiply back again after all that. Integrate that, gives me sine minus cosine, then I multiply by x, which is this, and it gives me that. And this, again, is C1 times that plus C2 is the homogeneous piece. And then after the dust settles, this is 0, and that's minus 1. It's kind of not too exciting, but there it is. The particular solution to this problem is 0, minus 1 by various parameters. Now it doesn't, here. There's an example. Well, let's look at another example before we put this away here. Maybe this will be more exciting. Number 16. Here. Oh, so I have the same coefficient matrix, but a different inhomogeneous term. So again, the fundamental solution matrix is that, the inverse is that. But now instead of integrating 1, 0, I integrate 8 sine t 0. And that integrates to, well, when you multiply it, you get 8 sine cosine, 8 sine squared. So integrating that gives me minus 4 cosine squared. Integrating that gives me minus 4 sine t cosine t minus t. And then I still have to multiply this after I integrate by the fundamental solution matrix. And so there you go. There's the homogeneous piece. And this is the particular solution that we derive from variation of parameters. So, like I said, even for 2 by 2 systems, these are kind of a pain. But it's a pretty simple algorithm, what you got to do, right? You got to find the fundamental solution matrix, multiply it by the inhomogeneous term, integrate that thing. Find the fundamental solution matrix, find the inverse of the fundamental solution matrix, multiply that by the inhomogeneous term, integrate the thing, multiply by the fundamental solution matrix, and then add it to the homogeneous solution, and there you go. That's the general solution. So now, of course, this gets much less pleasant when you get to 3 by 3 matrices, because then you actually have to find the inverse of a 3 by 3 matrix of functions to execute this method, which you can do, but not on an in-class test. I wouldn't do that. Okay, so there's that. Here's another one. So, behold. I think here, actually, I'm showing there's another thing that you can do. This is a formula in your book also. If you want to build in the initial condition, you can take the fundamental solution matrix at t, multiply it by the inverse of the fundamental solution matrix at time 0. And this is the initial condition vector. And then instead of integrating from 0 to t, integrate from like 0 to, instead of doing an indefinite integral, you can do a definite integral from 0 to t, integrate over a dummy variable s, And this will create the solution which has that as its initial condition. So there's a formula in your book for that, which is, it's not too hard to derive that formula. It's just basically the same algebra here. And then at the end, integrate from 0 to t. And I don't think I need to go through it for you. Let me tell you where it is. Where's that thing? So this is section 9.7. I am speaking at the moment of formula 13 on page 554. That's the formula I'm using here to build the initial condition into it. Again, this is the Fundamentals of Differential Equations, 6th edition by Nagel, Saff, and Snyder. This cost us tens of dollars. No, wait a minute. $10. $10. Okie doke. So, let's then move along here. Now I'm going back to chapter 5, actually. All right. So in chapter 5, he talks about what's called the phase plane, and he talks about elimination. So he talks about solving systems by what I would call brute force. I'm going to work an example for you guys and see if we can't understand it. Let's see here. I don't want to work a terribly difficult example. I'd like to find one that's not too annoying, but illustrates the idea here. All right. I'm going to try number 17. I may regret this. We'll see what happens. Maybe I should just make one up. Yeah, I probably should do that. No, fine. I probably shouldn't. Usually when I make stuff up, bad things happen. All right, so man down. There we go. So here's the problem. We've solved systems using matrix methods, right? Is there another way to do it? Well, yes. So here's the other way. This is number 17 from page 250 of your text. Doesn't really matter where it's from. Here's the problem. X prime prime, but plus 5x minus 4y. Actually, before I do this, I'm going to look at the answer. Because if the answer's got square root of 15 in it and square root of 23 and junk like that, I'm bailing on this early. Well, okay, it's not too bad. I think we'll be okay. It's got a square root of 6 in it, but the other one's integer, so I'm relatively happy. All right, so x prime prime plus 5x minus 4y equal to 0, and minus x plus y prime prime, right, plus 2y equal to 0. Now, this is what? This is a coupled system, right? I mean, the x and the y equations are interlinked. They're both second order, so if you want to think of like the total order of this problem, it's 4. If I was to reduce this to a system of first order differential equations in normal form, we'd be facing a 4x4 differential equation. That's kind of a pain. Is there another way to do these sorts of problems in terms of direct calculation? Well, yeah, there is. And it's sometimes helpful, sometimes not. So basically the idea is to use the d notation. So this is actually d squared plus 5, right, acting on x. Equals to 4y. And what else do we have here? We have d squared plus 2 acting on y is equal to x, right? See what I did there? And so you can do substitution at the level of these operator equations. So if we had a differential equation that just had x or just had y in it, we could solve it, right? So what? So what do we do? I mean, you got choices. You want to get rid of x or you want to get rid of y? Get rid of y. All right. Chose the hard one.
Get rid of X.
Thank you. So if we take this, right, and we just plug it in up there, right, what do we get? We get d squared plus 5, d squared plus 2, acting on y, equals to 4y. It ain't pretty, but now we can do algebra. So this is d to the 4th plus 5 plus 2, 7, d squared, right, plus 10, minus 4, acting on y, equal to 0. What?
I guess I'm just trying to follow why you can plug X in right there. 'Cause don't they mean, I guess they mean the same.
Well, that's the thing is, why do I get to use one equation and the other? It's because these are a pair. You know, we're trying to solve this system, right? So we're trying to find functions which simultaneously solve both of these equations. So it's legitimate to plug one into the other, yeah. But a justifiable concern. Now the question is, can you do algebra? Or really the question is, can I do algebra? Or if you can do algebra and you see it and you don't tell me, are you going to just leave me hanging here? I mean, I don't know. That's up to you guys. Are you good people? Are you bad people? I mean, I don't know. Who'd you vote for? So you don't have to tell me. You don't have to tell me. I'm just kidding. Let's see here. Do I need to end class early? Do you got to go riot or something right now? I mean, I don't know. I don't know what your schedule's like.
It's full of writing.
Full of rioting? Yeah. Yeah, I guess I remember those riots we had when Obama won his second term. Let's see here. Anyway, let's see here. Anyway, I think that factor is actually, right? Thank you. D squared plus 6, d squared plus 1. We have a winner. And so that gives me, I can read the solution right off of that, right? My solution for y is equal to c1 cosine root 6t plus c2 sine root 6t, right? Plus c3 cosine t plus c4 sine t. There's half of it, right? And you're like, I guess if you guys are paying attention here, you might be like, hey, I didn't need to learn eigenvectors and complexification. I could have just done this, you jerk. Why didn't you just teach us this? Why did you teach us all that eigenvector stuff? I don't know. They're different tools. I have had before, I mean, I do want you guys to understand both. Eigenvectors have application far beyond solving our little differential equations that we're doing here. But anyway, eigenvectors are important. But this is another method. And in a past semester when I wasn't as careful as I should have been, I had a student who never learned the eigenvector method, and she solved absolutely everything with this method. But it's not a good way. It really, I mean, it's a way, but it's, well, whatever. Teach his own. All right, so y is equal to 1/4, right? D squared plus 5, acting on x, you see. So all we have to do to find x is to do that derivative and add 5, right? So like, and divide by 4, all right? So that's 1/4. And what happens when you twice differentiate that thing? So like C1, 2 times differentiating brings out root 6. So it's minus 6 plus 5. C1 cosine root 6t. And then C2 minus 6 plus 5 sine root 6t. And then C3. And now when you differentiate that 2 times, you just get minus 1 times cosine, and then plus the 5 cosine t. C4 minus 1 from the twice differentiating, plus the 5 here, sine t. Close big bracket. Therefore, y is equal to, let's see here, minus 1/4 C1 cosine of root 6t, minus 1/4 C2 sine root 6 times t, and plus 4 cosine t, plus 4c3 cosine t, I should say, plus 4c4 sine t. And there you go. That and the x, there's the solution. I'm sorry, I'm an idiot. What have I done? What have I done? Aw, man, why'd you guys let me do that? Come on. Why'd you guys let me do that? Guys, no. No. Did I say no?
Yes.
This is nonsense. What if I, look, I don't know x. This is not, this is y. I should, no. This was and I'm very annoyed because I'm very proud of this calculation that doesn't mean anything, but like, this is so sad about this. You guys should have stopped me. It's fine. So I should solve. I have y. I just need to do this, right? Duh. Sorry. I'm an idiot. Right here, this one, right? That says that x, which I don't know yet, I just twice differentiate y and add twice itself, and that's my solution. All right, so by calculations very similar to the ones I just did more slowly, this is C1 times minus 6 plus 2 cosine root 6t plus C2 times minus 6 plus 2 sine squared of 6t plus C3 minus 1 plus 2 cosine t plus C4 minus 1 plus 2 parentheses sine t. Clean it up a little bit here. X of t is minus 4c1 cosine squared of 6t minus 4c2 sine of the root 6t plus c3 cosine t plus c4 sine t. Man, I thought I had such a nice calculation there before, but it was not at all what we were supposed to do. Anyway, really, so to summarize what I'm doing here, it's really just the same as what? Just systems of equations with substitutions, right? Just the substitution method, but instead of having just equations, we got differential equations. But the same song and dance, right? You eliminate one variable, you solve the differential equation, which results, and then you can plug that into the other differential equation, and out pops the answer. It sounds easy enough, right? In fact, that is the answer in the back of the book. Woohoo! All right, so that's elimination method for systems. Section 5.3 is on solving systems higher order equations numerically. You can go ask Dr. Wang about that. I'm not going to talk about it. So that brings us to our next topic, which is the phase plane. All right. So there's like one problem, I think, on test 2. I want to say on the take-home test, where it's a second-order problem. It's like a pair of second-order problems. If you have a pair of second order problems that are kind of like this is way, way faster than using eigenvectors, right? These problems are interesting, and they appear in things like if you had two RLC circuits coupled together, you get differential equations like this for the charge. Or if you have a pair of springs coupled together, you get equations like these. So these differential equations appear in systems of coupled springs and so forth, stuff like that. So, of course, this is actually sort of interesting. What this means is if you reduce this to a fourth order problem, like a 4x4 matrix in normal form, that matrix will have complex eigenvectors, two of them. One with complex eigenvector plus or minus I, the other one complex eigenvalue plus or minus square root of 6i. And that'll be that. That's what it would look like if we were to do it that way. But this is easier, right? So. So what's the phase plane? So this is section 5.4. Now, I have said some things in, I think, the take-home test too, about using p-plane. I mean, if you can figure out how to use p-plane in MATLAB, more power to you. I don't have MATLAB on my computer, and the way I was doing it before has Java problems, which I'm currently unable to crack. I go back and forth as time goes on, the Java, the website. But anyway, I have found new websites that I'll show you guys today that work for me anyway, that will do these things. So this is definitely this is not a solution technique we're going over right now. This is an example of qualitative analysis, all right? So, which is important, right? I mean, these problems we look at, sometimes you can find a quantitative solution. You can actually find a closed form algebraic solution of these things, right? But not always. And so it's important to also have other sort of tools in our toolbox that we can analyze a differential equation without actually being able to solve it. That's what this is about. So this kind of problem is what? This is what's known as an autonomous system. It's autonomous because these guys know t dependence. All right? So if you have an autonomous system of two differential equations, all right, then you can, you can analyze these a couple different ways. How to analyze? Well, one, you can plot the direction field. All right. You can plot the direction field with appropriate software and see what the solutions look like. All right. That's one thing you can do. Two, you can look for critical points algebraically. What's a critical point here? Critical points have dx dt equal to 0 and dy dt equal to 0. All right. So for an actual specific problem, we can look for those. Those are also helpful. Those are places where something funny happens in the solution set. You have lots of different solutions flowing together. The critical points can be stable. They can be unstable. They can be saddle points, unstable. Stable points usually have some sort of periodic solutions around them. There's all kinds of interesting things that happen at critical points. And then three, you can use the, what's he call it? He calls it the phase plane equation. You can use the phase plane equation to find curves whose parameterizations form solutions of the autonomous system. Let's call it star. Okay, so the solutions to this would be functions of time, right? the phase plane equation takes time out of the picture. It's really simple what it is. It's kind of funny. Today I'm teaching how to do calculus for parametric curves in Calc 2 of all things. So what we'll learn today is that if you want to calculate dy dx, right? And if you want to calculate dy dx for a parametric curve, what do? You calculate dy dt divided by dx dt, right? That's actually Calc 2 for me today. Haha, funny. Now, in the context of an autonomous system of differential equations, what is that? Well, dx dt is f, dy dt is g, right? So you just have to solve f of xy over g of xy. That's the so-called phase plane equation, all right? This is the phase plane equation. All right. I think I have some examples prepared for you guys over here. See if I can get them to work. So this is phase plane homework. It's posted on the website. I'll try to make an announcement for you guys that has links to these things. This and also the website I'm about to use. But here's some problems I've solved before that we can look at and make sure we get the idea. I mean, if I take too much time to work stuff out in here, you're going to lose the big picture of what we're doing. So it's better to kind of look at solutions together today. It's probably because of the election. Anyway, so sorry. So here's an autonomous system. First of all, you could look for its critical points, right? That's would be where both of these are 0. Actually, I have no sense of what that would be. I think there may be no critical points here because this can't be equal to 0. Because, oh, wait a minute. Well, I guess it might have critical points. I don't know. I'd have to plot it. We'll do that next, okay? Anyway, this is a system. This is an autonomous system. You can analyze it in part by finding the phase plane equation. So that's here, e to the x plus y divided by 2y minus x. Can you solve that? Sometimes you can solve it directly using like week 1 or 2 methods, separation of variables and all that, right? So can I do that here? Oh man, it's not obvious how to separate variables. I can't use the integrating factor. Oh, Nikes. Oh, do I win? Oh, I win. I was like, oh no, I can't do it. Apparently this is, oh, it's exact though. So after a moment doubt leaves me, and then I realize it's an exact equation, and so the integrating gives me this level curve, y squared minus e to the x minus xy equals to a constant. Those are the integral curves. So these parameterizations of these curves will be solutions to the original differential equation. Now, so the point of this is we don't really care what the formulas are, x of t, y of t, which solve the autonomous ODE. We just want to see what the solutions look like. And once you know this, you can do that. You can plot them using appropriate software. Now, okay, so let me just second here. So we're looking at, what is this? X prime, 2y minus x, y prime, e to the x plus y. All right. Let me go a step further than my solution. Let me show you. There's great websites these days to help you with qualitative analysis. And of course, you guys have access to MATLAB as well. So you could use the p-plane in there. It is a built-in function, I think, in MATLAB. But I found this thing. So check it out. Now, this, if I can make this bigger. So what was my differential equation? X prime was what? X prime was 2y. Usually you got to do like multiplication with a star and these sorts of things, right? Minus x, and downstairs, hopefully it's got, I don't know what it's, I'm not sure what e to the x is here. I'm going to guess I'm going to guess exponential x. I'm not sure, though. Let's see here. So these, what do these arrows represent? So every place I click, it plots a solution for us. These arrows, right? These arrows are like dx dt, comma, dy dt. They're the velocity vectors. They point in the direction dx dt, dy dt, as defined by the differential equation. And apparently there's a critical point right here. So I don't know. I think it's very cool. In contrast, you could, I suppose you could plot the level curve. You could look at the level curve directly if you wanted. There's also this here, slope field. What's the difference between slope field and direction field? Slope field we talk about in like Calc 1, right? You notice that what's missing? The arrows, right? This is the difference. The direction field has arrows, whereas slope field just has slopes. So we're interested in, direction fields. All right, so that's one problem. So here's another one. Solve the phase plane equation and sketch some integral curves. So here we have dx dt equals to 2y, dy dt equals to 2x. So the phase plane equation is x over y. This one we can do easier, right? You just integrate, you get y squared minus x squared equals to a constant. Them's hyperbolas, right? And I can actually plot that by hand. There's so there's what the solutions to the differential equation look like. And how did I figure out the arrows on the solutions? I mean, the Cartesian hyperbolas don't have arrows on them. There's no sense of direction, right? So how do I figure out the directionality of the solutions? You have to go back, right, to the differential equation here. See, dx dt is 2y. That means that x goes right when y is positive. So when y is positive, right, when y is positive, the solutions have to flow to the right. When y is negative, the solutions have to flow to the left. That's how I put the arrows on. I have to go back to the differential equation to decide the direction of the trajectories. Okay. Now, here's a critical point problem, which is kind of interesting. 2x plus y plus 3 minus 3x minus 2y minus 4. So the critical points, you have to solve those simultaneously being 0. And you end up with a solution minus 2, 1. Let's see here, just a second. If I had a better memory, I wouldn't have to write this down, but I do. So I think it's fun to take this, right? Because I ask you in your problem on the test to use phase plane to graph. You could use phase plane. You could use p-plane if you want, but you could also use like the website and just take screenshots and print it out. That's cool. Whatever. I'm not trying to, whatever's easiest for you, just do something. And you want to click some points so you have some representative solutions. Think about what makes a good picture of what you're doing. But here it is. 2 times x, right, plus y, plus 3, right? What's the other one? Negative 3 minus. I'm not sure I have to do the star. I'm just minus 4. Okay. And let's see here. We're looking at minus 5 to 5. Minus 5 to 5. Where was the critical point? 2, 1. So it should be in there. Okay. So. When I look at the arrows, it's not immediately obvious to me where things are, but once you start clicking these, it becomes, you can see, right? You can see exactly where something funny is going on. And right here is that critical point. This is that's that point. If you look, that's 1 in the y. And if I could scroll down here, minus what? It looks like minus 2 in the x, right? So there's a theorem for systems of differential equations that says away from critical points, right, and given reasonable conditions on the system, you just get a unique solution going through each point, right? There's just a unique solution. If I pick this point, how many solutions flow through this point? Just the one, right? But something different happens at a critical point, right? Something different happens there. So anyway, going back to my show and tell here. The other kind of problem to look at, and this is, I talked about this I think a little bit another day, but let me refresh your memory. This is the energy, we called it the energy lemma before. So the thing is, if you have a second order differential equation, right, you can make a reduction of order. And that will change it to 2 differential equations at first order, right? And if it's the kind of problems we look at, the ones that are corresponding to conservative forces, basically when you make the reduction of order, you'll get an autonomous system of differential equations. Like here's, so starting out with y prime prime plus y equal to 0, like that would be the equation for a spring with no friction, right? You make reduction of order, introduce y prime equal to v, you get dv dt plus y equal to 0. And of course you also have v is equal to y prime. So the phase plane equation here, see y is playing the role of y, but x now is played by the velocity. All right. So we have 2 differential equations, right? We have dv dt equals to minus y. Let me write them down. We have dv dt equals to minus y, but we also have dy dt, right, equals to what? V, right? So this is an autonomous system where, let's see here. So this gives us dy dv equals to, well, dy dt divided by dv dt, right? Which is what? V over minus y, right? So that's the phase plane equation for this problem. But now it has more physical significance because the phase plane is what? It's the position velocity plane. See, the velocity is playing the role of x. So when you look at the phase plane plot, the velocity is going to go this way. The position is going to... That's backwards. That's not how it's done. The velocity goes this way. The position goes that way. Meh. I think we may be running into some conventional troubles. Anyway, how you label axes aside. Of course, this you can solve, right? And you get v squared plus y squared equals to k squared. Now, if you tilt your head and squint, you can see that there's an m over 2 here, and there's a k over 2 here, and this is energy. This is really just saying that the energy is equal to a constant. That's the significance of the level curve in the phase plane here. The mass of this problem was 1. The spring constant was 1, so you have to use your imagination to see the m over 2 and the k over 2. Sorry. Anyway, here it is. So that's the... But you see I've turned the tables here, haven't I, though? Because v is playing the role of x, right? Usually we draw x this way. So my physicsy background is influencing me to draw it as physicists draw it, which is this way. We draw the velocity up, we draw the position over in these problems, just because, well, I don't know, there's lots of reasons, but mostly convention, right? Here's another one. Well, that one's not interesting. I want to get to one with a picture. Here it is. So here we have d squared x dt squared plus 2x squared plus x plus 1. That would be like a Newton's equation, right? And the significance of the 2x squared plus x plus 1 is that that's minus the force. All right? So the integral of that is the potential energy. If it's conservative, the force differentiated multiplied by minus 1, that's the potential energy when you differentiate it and multiply by minus 1 should be the force, right? So if I solve d squared x dt squared equal to f of x, that would be Newton's equation. The thing is, I've got the 2x squared plus x plus minus 1 on the same side of the equation as the acceleration. So you have to interpret that, physically speaking, this guy right here, right? This term is minus the force. See, if I put it on the other side, then it would be net force. So if it's on this side, it's minus the force. Which means that I can just anti-differentiate it to get the potential energy. Because the potential energy, when you differentiate, you still have to multiply by minus 1 to get the force. This is how physics works. Right, that pesky minus. So anyway, this is the potential energy corresponding to the force for the problem. And so using the phase plane idea, we have v is equal to dx dt, we've got dv dt is equal to this. So the phase plane, eliminating time, right? I mean, you could do that, but the thing is, the other way of analyzing, you can analyze it directly. This is the trick. You can plot the, excuse me. So, I guess I haven't worked out the theory enough in here. My stupid. I may need to go to my notes to explain this. Just a second. Oh, seriously. They can't stop me. It's on my own computer. I will find it. The question is what semester? Sorry. I'll get over it. What page were we saying it was? I want to say it was that one. Yeah, that should be it. Let's see here. Well, that link is bogus. Yeah. Maybe this is a sign I should go on the Laplace transforms. Sorry, I actually tried to find this before class and then I got distracted with that conversation. I see now that there's a, I'm looking for, there's a P-plane PDF in here somewhere. As soon as I can find it, we'll be good.
Professor,
Yep.
I think your computer's on airplane mode.
Yay. Thank you. We win, I think. Well, here we go. So, again, I'll provide a link for this here. I'm annoyed. The edition of the book that you guys have is unfortunate. There's a whole chapter in the book on critical points and the phase plane analysis. There's a much longer chapter in the edition of the book I used when I wrote these notes, chapter 12, that's missing from your book. So there's just a shortened version in chapter 5. So this is probably helpful to you to fill in some of what's missing in your book. I don't think I've tested you on it that deeply, but I think it's interesting. I mean, these are the different kinds of critical points that you can get. You can get asymptotically stable. You can get an unstable spiral. You can get an unstable saddle. You can get just a stable center, which has these nice elliptical orbits around it. That would be like the phase plane for a spring. Here's like a phase plane for a spring with friction, right? It spirals in. Eventually, it just stops and sits there. And unstable spiral will be that. Anyway, in here I derive. Here it is. Come on. Where's my derivation? Dang it. I'm sorry, guys. What a stupid thing. Maybe I don't have a derivation. I'll just, here's an example anyway. So you start with the second order differential equation, in this case the spring, and that gives us the, basically this is the phase equation when you separate the variables, and then these are the integral curves to the phase equation, which correspond to constant energy curves for the harmonic oscillator. It's still not what I want to show you, though. Dang it. I'm sorry. I'm just going to have to... I mean, I guess I'll just have to hear. The point... Sorry. I'm something stupid I'm not finding the words for at the moment. I guess I just have to work it out. So, all kinds of stuff can happen for these generic problems, but when we look at problems which are coming from physics, it's much less, there's much less freedom. So if we have d squared x dt squared, right, is equal to the net force. Let's start there. This is equal to minus the derivative of the potential energy dx, right, if it's conservative. So the point is that if you make the variable, if you make the substitution, if you let v equal to dx dt, right, then you have this system. You have on the one hand dv dt equals to minus du dx, where this is the potential energy. You also have that dx dt is equal to v, right? So this is the autonomous system that corresponds to Newton's equation, right? Then the question is, what are the critical points? What are the critical points for such a system? What was the critical points for this autonomous system? It's a very specific and special case. And if you look at it, well, we need what? We need two things, right? Ooh. We need this equal to 0, right? And we need that equal to 0 for critical point, right? So what does that say? That says v is equal to 0. So the critical points in the phase plane for that autonomous system, they have to happen wherever, you know, on the v equals 0 curve in the plane, right? And also, du dx has to be 0. What does that say? In other words, x is critical for what? X is a critical point of u, the potential energy. So what this means is if you draw the potential energy plot, right, for the system, from the potential energy plot,